In this video, I'm going to take you through how to start with an ISETBio scene and compute the photoisomerizations in each of the cones in a simulated human cone mosaic. Let me share my screen. Just to orient you, you should have ISETBio installed on your computer and on your Matlab path, and then we're working through LiveScripts in the ISETBioLiveScript repository. This script builds on a script that is discussed in a separate video, LiveScript scene for the stimulus on display, which is here in the ISETBioLiveScript tree. And now we're going to work through the LiveScript cone isomerizations from scene on display. So I have that script here. And in step one, we basically repeat what was done in the script that described how to produce a scene for a Gabor patch. So I'll go ahead and evaluate this section, which produces for us a Gabor patch scene displayed on a Apple LCD display. Here's a rendering of the Gabor patch. I think in this case it's 15 cycles per degree. And here are renderings of the spectral radiance at different wavelengths in the visible spectrum. You can see the variation with wavelength as it's rendered using the LCD display's primaries. And those pictures are over here in the side of the LiveScript once you want to run it. Now, given we have an ISETBio scene, what we want to do next is compute the retinal image, which in ISETBio terminology, we call the optical image. And so the first thing we have to do is set up a structure which describes the optics of the eye. And we're going to be using a description based on wavefront sensor measurements of human eyes. And so the first step here is to create the optical image object, which I'll do right here. And that object, when we go with the default WF for wavefront human measurements, contains descriptions of the pupil function of the eye, which in turn allows us to compute the point spread function separately for each wavelength. So this incorporates chromatic aberration and aberrations in the eye measured using wavefront optics techniques. The particular Zernike coefficients we use to describe the pupil function are sort of a typical human that we described or extracted from data reported by Larry Tybos's group. And the details of that are available in a forthcoming, or actually in a published paper that we describe how we chose a typical quote unquote subject from that. Now, in the optics we've set up, there are essentially point spread functions and optical transfer functions in the frequency domain, so we can look at those just using these two pieces of code here. So here at 550 nanometers, where things are in pretty good focus, we get a fairly sharp point spread function for this subject. And here's the modulation transfer function as a function of spatial frequency corresponding to that. But at 500 nanometers, things are more aberrated, and the point spread function is got more idiosyncratic characteristics, and the modulation transfer function falls off more steeply than at 550 nanometers. You could look at that at other nanometers, other cases as well, but those are the two shown here. And the visualization code is right here, picking out the wavelength that we want to see. Now, given that we have the optics set up, actually it's a very simple matter in terms of code to compute the retinal image. We just use the optical image compute method on the optical image, passing to it the scene, the ISETBio scene that we want to render. And so we can just do that as that little one-liner. And this calculation is done at each wavelength, so we can visualize the result. Here we see the number of different views of this. In one view, we just see the image itself rendered as an RGB image, and it looks a little yellower than the original, and that's because the computation of the optical image in terms of the way we do it incorporates absorption by the lens, and that absorption is stronger at shorter wavelengths than longer wavelengths. And so when we just render as an RGB image, the retinal image, it does not have the same color appearance as the original stimulus. We can also look at that as a function of wavelength, seeing that chromatic aberration has blurred the image considerably more in the short wavelengths, where you can hardly resolve the grading, than at the in-focus wavelengths, and that's because of chromatic aberration, which is incorporated here. We can see that in a slice view of the stimulus as well, where the amount of contrast is highest at near in-focus wavelengths and decreases moving away from that in either direction because of chromatic aberration. So those graphs are then stored in the LiveScript style over here at the side. And so we're about there to the figures. Now, having computed the retinal image, we want to now figure out what the cone responses to that would be. And for that, we need a simulated cone mosaic. Here we're going to use a mosaic built on an algorithm developed by Nicholas Kateris, where we try to match the eccentricity varying density of the cones along with other factors in the mosaic that vary with eccentricity. So the first thing we do is we set up the parameters to describe that. And the cone mosaic hex object is the way we do that. And it takes some detailed factors having to do with setting up the mosaic itself and the algorithm, the field of view in degrees. We're going to let the eccentricity vary, density vary with eccentricity. We're going to let the quantum efficiency vary with eccentricity because the cone apertures and outer segment length varies, and we have that modeled here as well. We're going to actually specify a integration time, which here looks like it's in fact 30 milliseconds, although it says 5 here and 20 there. That's an error. Maybe I will fix both of those things to make it all consistent. That will determine the amount of Poisson noise in each frame. And then this is, again, is another algorithm specific parameter. So I'll do that. And then once we have the parameters, it generates a mosaic. That takes a little bit of time. It's iterating around, moving cones around, trying to match the specified density, which we take from some measurements by Christine Curcio. In the default configuration, as we'll see, there's going to be a tritanopic area in the mosaic, and there's going to be, with no S cones, and the LM cone ratio is going to be approximately 2 to 1. I think if we can scroll down here, we can see some of that. Let's just execute this next code where we generate 2 different noisy instances of responses to our scene from the mosaic and visualize the results. Okay, so what we see here in this figure, which I'll make a little larger here, is first here's the patch of mosaic, and you can see a couple things. First of all, it's more or less hexagonally packed in the center. This is a foveal mosaic. There are no S cones, which are indicated by the blue in the very center, approximately 20 minutes of arc. And then we've got blue cones coming in a quasi-regular fashion. You can see the cone apertures are getting a little larger as we go out from the fovea outwards. So that's capturing that feature of the human cone mosaic packing, and therefore the density is going down as we move outward. And here are now just 2 depictions of cone mosaic responses to the Gabor scene that we set up. And they're a little different from each other because in each case there's Poisson noise added to the photo excitations, the isomerizations that are computed, and that Poisson noise models the stochastic nature of photo absorption, and the integration time determines the signal to noise ratio of that Poisson noise because the number of mean isomerization goes up the longer the integration time is. This is just a little slice through what you might get for 10 different instances of the excitations per individual cones as one moves across some band here, picking out the nearest cone as you go across with the color indicating the type of the cone. So we have the L, the M, the L, the M, and the S. The S cone responses are considerably smaller, largely due to that short wavelength absorption in the lens that I mentioned previously. So you can see that the Gabor structure is visible here, even in this single cone by cone representation, and certainly visible here for this high contrast Gabor. In fact, the code that does that visualization for the 10 excitations is shown here. It also produces this graph, which is just, if I can get zoomed, and well, here it is over here. Show it to me. This is just at different Y positions as you move down. This image here is another visualization. You can see the profiles across different different cone excitations and get a sense of the noise relative to the signal, as well as the variation along the y-axis. So that's basically the script and these calculations. One other thing that I wanted to point out in the calculation itself is that when we did the calculations, we had the option of putting in a eye movement path that would jitter the position of the retina relative to the stimulus. And here we put those in as 0, so there are no eye movements. Somewhere else, another tutorial will show how you could actually model eye movement and generate realistic eye fixation paths.